All right, my friends. So for part A, what's so improper about it? I claim it's the zero that is improper. And so I will rewrite this one as the limit as A approaches zero. And from which side would you be approaching zero? Well, think about, the idea of area behind this. Your region would start at zero and go to one. So your region would be approaching zero from the right side. So and then of the integral from a to 1 of, and I'm just going to rewrite this integrand as x to the negative 1/2 dx. There we go. Okay, so then from here, let's use power rule. So add 1, divide by the results. So we'd be left with the limit as a approaches 0 from the right of, let's see, 2 times the square root of x, essentially, and then from a to 1. Okay, what would that equal? That would equal the limit as a approaches 0 from the right of 2 times the square root of 1 minus 2 times the square root of a. Okay, and good thing we're approaching 0 from the right because the double-sided limit on a square root function doesn't exist. And so let's evaluate the part you can. So that's just equal to 2. And then really you just have to worry about this part. There we go. Okay. And so let a approach 0 from the right. You can totally square root of this little tiny positive number and your answer would approach 0. So this part should approach 0. So you'd be left with 2 minus 2 times 0, which would just be 2. There we go. It just said to evaluate the integral, so we're done. If they said, does it converge or diverge, we could say it converges, and we could even be fancy and say it converges to 2. All right, let's take a look at part B. Oh, part B is a tricky one. Okay, so first of all, it's doubly improper. It's improper because of the 0, and it's improper because of the infinity as well. Oh, good. Okay. Let's see. There are different ways to show your work for these. How do I want to demonstrate that? Let's see. Let's do. Okay, I'm going to do a combo. I'm going to do. All right, the limit as I'm going to do b approaches infinity. And then instead of doing another limit statement for the 0, I'm going to do this move. So we're approaching 0 from the right. And this would take care of the same. That's another way of taking care of this limit statement as well. Just a little, a little less PhD like. But for a problem like this, I really prefer it. And then I'll use b for the upper bound. Now for the integrand, which is really where this one's tricky, I'm going to start by kind of pulling the dx off to the side because that's where I like them. I'm also going to pull the 1 over square root x off to the side. And then for this part, I'm going to rewrite it as the square root of x squared plus 1. I'm writing it that way because I do see this one as potentially an arctangent function. So from here, if I was to let u equal the square root of x, then my du would be 1 over 2 square root x dx. Maybe now, if you weren't sure what I was up to a second ago, maybe now you can see it. So 1 over square root x dx is equal to 2 dus. Yep. Okay, so let's see. So what would we have? We'd have the limit as b approaches infinity of, I think I'm going to worry about the bounds in a second here. So I'd have 1 over u squared plus 1, and then times 2 du. I think I'm just going to, for now, put the 2 there. And instead of pulling it up front, even though it doesn't really matter. And then let's see. Oh, goody. So let's see, lower bound. Let's pay attention to that. If x is equal to 0 from the right, then u would equal square root of this number from the right, which would basically just be 0 from above. So that stays the same. If x is equal to b for your upper bound, then u would equal the square root of b. There we go. Okay. All right. So now let's finish this out. So this 2, you could pull in front of everything if you want. It's a constant as far as everything is concerned. So I'm just going to go ahead and do that. And then we'd have the limit as b approaches infinity of arctangent of the square root of b minus arctangent of this number a smidge to the right of 0. Okay, so we'd be left with 2 times, and now let's figure this out. So if b approaches infinity, square root of infinity is still going to infinity, and then arctangent of a number approaching infinity is pi over 2. Arctangent of 0, a number infinitely close to 0 from the right side, is still just 0. So you'd have 2 times pi over 2 minus 0, which means you end up with just pi. There we go. And we have evaluated it. Okay. Let's see. Let's talk about this special type of improper integral right here. So if you have an improper integral where its lower bound is 1 and its upper bound is infinity, specifically 1 to infinity, and it's of the form 1 over x to the p dx, where that p value there is a constant, it will actually end up equaling 1 over p minus 1 as long as your p value is bigger than 1. But if your p value is less than or equal to 1, then your integral will diverge. And let's talk about the second part here for a second. I do hope it makes sense that if your p value is a 1, that it would diverge, because that was the very first problem that we did. So there you go. And so if your value is 1 for p, you'd have a 1 over x graph. And the idea is that while your heights were approaching 0, they just didn't approach 0 fast enough. And so your integral would diverge to infinity. Now, if your p value, let's come back down here. If your p value is anything less than that, so you know it diverges if p is a 1. If p is anything less than that, like imagine p being a 0, then you'd have x to the 0, which is 1. So your integrand would have been 1. So imagine that one, right? So, of course, that would diverge. If your p value was a negative 1, then you'd have, y equals x as your graph. And so, of course, that would diverge. So hopefully it makes sense that the threshold for convergence or divergence is 1. So if your p-value is 1 or less, then this would diverge to infinity. And then if your p-value is greater than 1, then you'll get the answer will just be 1 over p minus 1. Okay. And I know I'm not proving that, but we will at least give you a chance to digest it here in this last example for this lesson. Okay, so for example 6, determine whether each interval converges or diverges. If it converges, evaluate it. So see how it goes. Check in with me in the next video.